Okay. Standard state. Okay, so enthalpy, delta H. Okay, it is sensitive to external conditions. Okay, and internal. It's very sensitive. Okay, small changes can make a big difference to your measurement of enthalpy. So, um, it takes it takes energy to change the temperature of something. Okay, remember you put heat in to get the temperature to go up. You lower the temperature, it's going to release heat. It takes energy to compress a gas. It takes energy to melt a solid. Okay, any sort of change, any physical change, is going to be reflected in the enthalpy that you measure. All these changes are going to be reflected. So, for example, here we have the combustion of propane. Okay, gas propane plus gaseous oxygen makes gaseous CO2 and gaseous water. Enthalpy for that change is 2044 kilojoules, negative. Okay, meaning that when you burn propane and it produces gaseous carbon dioxide and water, it will also release 2044 kilojoules of energy. But if you burn propane and oxygen to produce gaseous CO2 and liquid water, okay, notice the L, it will instead release 2,220 kilojoules of energy. That's an additional additional 70, 80, 76 kilojoules of energy. 176, there we go. I can math. All right. So, oops. Hello, kitty cat. So, what that means is that bad connection. Sorry, guys. It's going to be a buffer-heavy episode. Sorry about that. In any event, what that means is that we have to be very careful about the state of matter. So, the reason that this reaction releases 2044, this reaction releases 2220, is because you have to put extra energy in order to boil that water. Okay, if instead you produce liquid water, then you have that much more energy being released as, this enthalpy change, rather than being used to convert liquid water to gaseous water. So when we look, in the table in the back of the textbook, you'll notice that the enthalpies that are recorded back there are recorded as being at standard conditions. That way, you always know what conditions, what state of matter, what sort of situation you're talking about. And then you can adjust from there as needed. And standard conditions have been set so that you don't really have to do much adjustment. Okay, it's 1 atmosphere of pressure because we typically live at 1 atmosphere. It's 1 molar concentration because, that's convenient for reasons that don't matter too much right now. And it's usually 25 degrees Celsius, room temperature. Of course, for some people, room temperature is 20 degrees Celsius. And sometimes standard conditions is instead 0 degrees Celsius, because if you have ice, it's easy to keep things at 0 degrees Celsius. Okay, look. Standard conditions are only standard for a given value of standard. It's not always easy to tell. So if you're, Googling things, looking things up online, check the table. They'll list what they mean by standard conditions. 1 atmosphere pressure, 1 molar concentration, that's pretty universal. The temperature can vary, and temperature can make a difference. You have to put energy in to heat things up. You get energy out to cool things down. It makes a difference. But we report things as being at standard conditions, okay? And we pay attention to that, okay? But we note it with the little dot, okay? So you'll see a superscripted dot, okay? So delta H without the dot means enthalpy under some conditions. Who knows what? You'll have to be told. But delta H with the dot, that means standard enthalpy. It's much better. Okay. And that means that enthalpy is being reported at standard conditions. Okay. Whatever those standard conditions might be. 1 atmosphere, 1 molar, and probably room temperature? Probably. So delta H standard. Standard enthalpy, standard internal energy, standard entropy, standard Gibbs free energy. Okay, these are all things that can be recorded at standard conditions. We do that because it's actually relatively easy to take things away from standard conditions. We have methods for finding out, if you're working at, say, 35 degrees Celsius and 0.75 atmospheres and blah, 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 blah. It's relatively easy to get from standard conditions to whatever your conditions are, when you have to. Okay, for the most part, we won't. But those are standard conditions. For the most part, standard conditions won't come into play too much in this class in terms of, the practical effects that it has. But it could have some impact. And if nothing else, this is something they could ask you about on the test. Just what are standard conditions? Which of the following is standard conditions? Just to be absolutely certain what they expect you to know, double check the textbook. Okay. I'm accustomed to 25 degrees Celsius. The textbook might say something different. Okay, so double check the textbook. Okay. That way you'll know. If nothing else, you'll have something to complain about. All right. So, any questions about standard conditions? Okay. Let's continue then with enthalpy of reaction. So, delta always means final minus initial, regardless of what you are talking about. So, doesn't matter what the process is, enthalpy is a state function, and that means that the path doesn't matter. So, for example, solid water melting to liquid water has an enthalpy of fusion change 6.010 kilojoules per mole. That is to say, it takes about 6 kilojoules of energy to melt 1 mole of water at 0 degrees Celsius. Boiling water, likewise, meanwhile, I should say, going from liquid to gas, has an enthalpy of vaporization of 40.660 kilojoules per mole. It takes a little more than 40 kilojoules of energy to boil 1 mole of water at 100 degrees Celsius. So, what is the enthalpy of sublimation for water? Remember, sublimation means you're going from a solid directly to a gas. Therefore, means you're going from here to here. Oops, come on. From solid to liquid, liquid to gas is the same thing as going from solid to gas in terms of path. Going from A to D. Or going from A to C, I should say. Meaning that what we're doing is we're adding these two reactions together. So let's flip on over. There it is. And you'll see what I'm talking about. All right. So adding reactions together. Okay. Anything that appears on both sides of the arrows cancels out. So the liquid water is an intermediate phase we don't care too much about. So that the result is H2O solid going to H2O gas. So if reaction 1 plus reaction 2 yields reaction 3, then enthalpy 1 plus enthalpy 2 yields enthalpy 3. Okay. So in order to find the enthalpy of sublimation, we just add the enthalpy of fusion and the enthalpy of vaporization. So we come back here. These two reactions added together yield the one we're looking for. Therefore, these two enthalpies added together give us the enthalpy we're looking for. So 6.010 plus 40.660. Ah, crap. All right, there was just a slight delay. Gives us 46.670. The enthalpy of sublimation of water is 46.670. And this is true for pretty much any substance. The enthalpy of sublimation is just the enthalpy of fusion plus the enthalpy of vaporization. You just add those two together. It always works. Now, granted, there's going to be some small deviations because fusion takes place at one temperature, vaporization takes place at another temperature. So, I mean, it's technically kind of a fudge, but you know, we give that a wink and a nod. We ignore that. All right. So, how much energy is needed to melt 23.49 grams of ice at 0 degrees Celsius? This is, you know, a fairly simple problem. Okay, the enthalpy of fusion, you know, the amount of energy needed to melt ice is 6.010 kilojoules per mole. 23.49 grams of ice. We convert that to moles, and then we multiply that by the enthalpy of fusion. So, 23.49 grams of ice divided by the molar mass of ice, 18.02 grams per mole, gives us 1.304. So that's how many moles of water we're looking at. Then we multiply that by the enthalpy of fusion, 6.010 from the previous slide. And our answer is 7.834 kilojoules. Not necessarily, you know, deeply meaningful to you, but that is the answer to the problem. All right. How much energy is released by the condensation of 1.281 kilograms of water vapor at 100 degrees Celsius? This is, you know, just the reverse of this reaction. If boiling water, you put energy in to boil water. If you condense the water, you're going to get that energy back out. Okay. So it's just the exact same amount, but you flip the sign. So if you have to put in 40.660 kilojoules of energy to boil 1 mole of water, then when you condense 1 mole of steam, you're going to get 40.660 kilojoules of energy back out. So exact same thing, but with a negative sign. All right, so how much energy is released by the condensation of 1.281 kilograms of water? Exact same sort of problem. 1,281 grams divided by 18.02 grams per mole means we have 71.09 moles. Then we multiply that by, technically negative 40.066 negative means we're going to get 2,848 kilojoules of energy back out. That, by the way, is why steam is actually more dangerous. They say it's because, the steam can be any temperature. It can keep on going hotter and hotter. And that's technically true. But when it's escaping from the pot, it's escaping from the source of heat, so it's not really heating. The real danger from steam is that it will condense on your hand. Your hand is cooler than the boiling point of water. So it'll condense on your hand and release a ton of energy into your hand, or whatever else it condenses on. That's really why steam is more dangerous. In terms of, a pot of boiling water above the stove. If you're talking about steam pipes, then yeah, that steam can be super ridiculously, incredibly hot. So it depends on the situation you're looking at. Double checking, no questions. Let's continue. So, enthalpy of reaction. It's just the delta H for any given reaction. Okay. So, when aluminum metal reacts with rust under standard conditions, the result is aluminum oxide and molten iron. Will the following reaction be exothermic or endothermic? So note that I'm being kind of tricky with this one, because I reversed the reaction. Here we have iron and aluminum oxide making rust and aluminum. So I just flipped it around. When aluminum metal reacts with rust under standard condition, the result is aluminum oxide and molten iron. So the reaction that I described here is going to be exothermic, highly exothermic, molten iron. Iron is not normally molten under standard conditions. So it's incredibly exothermic. So exothermic that instead of producing solid iron, it produces liquid iron. Okay? So when you flip the reaction around, iron plus aluminum oxide, that is going to be an incredibly endothermic reaction. Okay? If you're going from rust and aluminum to iron and aluminum oxide is incredibly exothermic, then the reverse reaction is going to be endothermic. Okay? That's what I'm trying to hammer home here. Similar to how I did this, okay? Releasing energy through condensation. I'm trying to emphasize that if the reaction is exothermic in one direction, it is endothermic in the other direction. Remember, there is nothing in a chemical or a compound or a solid, a liquid, a gas, anything that says I am a product or I am a reactant. No, they don't have those little labels. They're just little doodads. They're atoms and molecules and so on. There's nothing stopping a reaction from proceeding in the reverse direction. It might be incredibly unlikely, as in this case. This is an incredibly endothermic reaction. It really doesn't want to proceed in this direction as written. It would much prefer to go, from aluminum and rust to iron and alumina. Okay, but it could happen. Okay? And thus, we talk when we're dealing with enthalpies and so on. We flip reactions, we multiply reactions, we do all sorts of things. And when we do that, we also alter the enthalpy. Okay? So by flipping this reaction around, making it backwards, it went from exothermic in one direction to endothermic in the other direction. So, how much heat is evolved by burning 10.32 grams of ethanol. The enthalpy of reaction is negative 1366.8 kilojoules. Okay, first note, when reporting standard enthalpy of reaction, we don't always say per mole, just because it's assumed. It saves a little bit of time, but it should always be understood to be there. So, how much heat is evolved by burning 10.32 grams of ethanol? Well, in order to check that out, we are going to need to look at the balanced reaction. So, let's hop on over to this guy here. Okay, all right. Come on. All right, so ethanol is C2H5OH plus oxygen, because we're looking at combustion, makes CO2 and H2O. Now we need to balance. Ooh, that's an ugly 2. All right, so we'll need 4 of these, 6 of these. 8 plus 6 is... Oh, no, we don't need to do that. All right, so 2 of these, 2 of these, 3 of these. 4 plus 3 is 7, so we need 3 of these. Okay, now it's balanced. All right. So the question was, how much heat is evolved, that is released, by burning 10.32 grams of ethanol? So the molar mass of ethanol is... 'll do this on my calculator. It's going to be about 45. $46.069. Whoa. Okay. So 10.32 grams, was it? Yes, 10.32 grams. So 10.32 grams divided by 46.069 grams per mole. Zero 0.2240. Oops, that's a 2 moles of ethanol. All right. Now, this is where things can get a little bit complicated, okay? Because the kilojoules for this enthalpy of reaction means that every time the reaction occurs, it releases 1366.8 kilojoules of energy. Meaning that every time this happens, okay, every time one molecule of ethanol reacts with 3 molecules of oxygen to produce 2 molecules of CO2 and 3 molecules of water. Well, moles, I should say, moles of but anyway, it's going to release that 1366.8 kilojoules. So the kilojoules per mole means kilojoules per unit reaction. So let me clear up some space so you can see what I'm talking about. So if you were to burn 1 mole of ethanol, it would release 1,366.8 kilojoules of energy. If you were to burn 1.5 moles of ethanol, then it would release, let's see, somewhere around 2,000 kilojoules of energy. Okay. And if you were to burn enough ethanol to react with 3 moles of oxygen, that would be 1,366.8 kilojoules of energy released. Okay. It's not really, strictly speaking, negative 1366.8 kilojoules per mole. Instead, it's negative 1366.8 kilojoules per unit reaction. So if you were to sort of write it out, it's always going to be sort of normalized to the coefficient of the compound in question. Okay. 1,366.8 kilojoules for every 1 mole of ethanol, or for every 3 moles of oxygen, or for every 2 moles of CO2, or for every 3 moles of water. Now, in this case, we're talking about ethanol, so it's going to be a nice, simple one, but it's something I wanted to try and emphasize early, because that is an easy mistake to get caught up in. Okay. Not remembering to keep that in mind. So we have 0.224, think. Yes, 0 moles of ethanol multiplied by negative 1,366.8 kilojoules of energy for every, and then we just grab our coefficient, bring it down here, 1 mole of ethanol. And then we hop into our calculator again. Don't forget the negative sign. Negative 306.2 kilojoules. Okay. So if you burn 10.32 grams of ethanol, that's 0.224 moles, and it will release 306.2 kilojoules of energy. So let's pause a moment for questions. All right, appears no questions, so let's continue. Another example. How much energy is needed to split 29.284 grams of water? Here we have an enthalpy of reaction. Going from 2 hydrogen plus 1 oxygen yields 2 molecules of water. Enthalpy is negative 471.6 kilojoules per mole. All right. Note again, I am being a little bit tricky. This reaction is backwards. I asked how much energy is needed to divide that much water. So this reaction is talking about combining hydrogen and oxygen to make water. So dividing water is the reverse of this reaction, and therefore the enthalpy will be reversed. If you release 471.6 kilojoules of energy per mole of water to make water, then you're going to need 471.6 kilojoules per mole to make that much water. So once again, we bring up our calculator. 29.284 grams, 18.02 grams per mole means 1.625 moles of water. But now this time, our enthalpy is not based on per 1 mole of water, it's based on per 2 moles of water. So when we do our math this time, hey, hey, Gardner McKay, take us on the leaky tinky with you. Oops. All right. Okay, so when we do our math this time, it's 1.625 moles of water times positive, because remember, we reverse the direction, 471.6 kilojoules per 2 moles of water. Because it's 471.6 kilojoules every time that reaction happens as written. And when the reaction happens as written, it splits or produces 2 moles of water. Okay. So now when we do this math, we multiply by 471.6. We multiply by 471.6, and then we divide by 2. Okay. So you need 383.2 kilojoules of energy to split the 28-ish grams of 29.284 grams of water. Don't forget to use the coefficients when you're doing this sort of math, when you're doing enthalpy of reaction math. Otherwise, you'll be off by a factor of 2 or 3 or whatever. All right. So those are enthalpy of reactions, and that is some of how you have to work with reactions. Remember, when you flip a reaction, you flip the sign, and when you are trying to find out how much energy is needed, you need to use the coefficients from the reaction. All right, and with that, we finished yet another set of slides. We will come back in about 5 minutes to talk about Hess's law, and then no, we'll just do Hess's law by itself. Hess's law is surprising. Okay, so we'll come back in 5 minutes to talk Hess's law. So I'll see you at 2:45.